In today's video, we are going to look at this worksheet and complete some of the problems in the worksheet. I'll complete one of each of the different problems. There's an example problem right here of determining formulas of hydrates as well. And I also made a video on your lab, the copper 2 sulfate hydrate one, and the problems are similar. Okay, so let's take a look at this first problem. It says a hydrate of magnesium sulfate has a mass of 13.52 grams. The sample is heated until no water remains. The magnesium anhydrate has a mass of 6.60 grams. So just note, anhydrate means without water, so it's just the salt or the ionic compound by itself. It says find the formula and name of the hydrate. So let's work our way to start this problem with this, okay? I wrote it all out as a way to kind of pace you through if you need to. So we're finding the formula of our hydrate, and our hydrate looks like this. It's got magnesium sulfate and it's got water attached to that. There's X and Y. X is the moles of magnesium sulfate, Y is the moles of water. Now, you're given the grams of magnesium, the anhydrate, which is the magnesium sulfate, and you want to convert that to moles so we can find our X. So here you have the conversion from grams to moles using the molar mass of magnesium sulfate. So then, just to remind you, that is our X that we just solved for right here. This is your X. Now we go to the next step. We need Y. To solve for Y, we need water. And to know how much water there is to do a little subtraction. And so we do know that the mass of the hydrate is 13.52 grams. And then the mass of our ionic salt by itself without the anhydrate is 6.6 grams, like it was stated earlier. You take the difference between the two and you'll see the mass of the water. And of course you convert that to moles using the molar mass of water, and that will give us our Y. Once we have our X and our Y, we then substitute it into the formula, like our original formula right here, our hydrates formula. And we'll notice that this formula doesn't look like a whole number. So to make this a whole number, what we do is we divide it by the lowest molar value. So between the two numbers, which one's a lower molar value? It's this one, the magnesium sulfate. And so when you divide both sides by the lowest molar value, you'll end up with a ratio that gives you 1 here, which is the whole number that we wanted to achieve. And then this works out to be a really nice number, whole number, which is 7. So the formula of the hydrate is for every 1 mole of magnesium sulfate, there's 7 moles of water attached to that. And we name it, it's called magnesium sulfate, like you would normally name an ionic compound. And then hepta means 7, and then hydrate means water. So that's how to name that hydrate. So now we go to the back side of our worksheet. On the back side, we're now going to talk about empirical formulas. So empirical formulas, by definition, is the lowest whole number ratio. So let me go ahead and write that definition out for you. It's a formula where you're looking at the lowest whole number ratio that is possible. Okay? So if it's a multiple, then it's called a molecular formula. If it's a lowest whole number ratio, it is called the empirical formula. So if you look at this substance right here, C6H6, notice how the 6:6 ratio between carbon and hydrogen is in fact reducible. It can be reduced down to a 1-to-1 ratio. Let me zoom in just to make sure you can see that a little bit better. Okay, so, and if you look at this next one, this is a reducible ratio too. A 2-to-6 ratio can be reduced down to a 2-to-6 can be reduced down to a 1-to-3 ratio. Just like a 6-to-6 ratio can be reduced down to a 1-to-1. So because it's reducible, these formulas are called molecular formulas. Now look at this ratio. Does a 3 to 8 ratio reduce any further as far as whole number ratios? It doesn't. So this is called the empirical. So we circle where we see an empirical formula. And we continue to circle all the way through from A through N, okay? I'm going to jump over to these problems now. In these problems, it says to find the percent composition by mass of A, F, G, and H. So it's compounds A, F, G, where's G, and H. So those are the 4 compounds you want to find the percent composition for. And so I'll show you how to do that. To find the percent composition, we zoom back out. By mass, what we're looking at is we're given the formula, and it's C6H6. This is A. We're looking at problem number A and finding percent composition by mass of that. And we remind ourselves that percentages have always been based on this part over whole idea, times it by 100. And that will give us our percentage in the end. Now, if you break this compound out, there's 2 components to this compound. There's carbon, to find the percent by mass of carbon, and there's also hydrogen, so percent by mass of hydrogen. So if you look at the work here, what I did was the part that I'm looking at is carbon. So I'm going to take, there's 6 moles of carbon. Each mole of carbon has a mass of 12.01, so there's 72.06 grams total of carbon. The total mass of the whole compound, called the molar mass, by the way. So really, this whole is really the molar mass. So the molar mass of the whole compound is 78.12, and we find that from the periodic table. These 2 values are found from the periodic table. Again, this is because there's 6 carbons. That's why this mass is so 6 times 12.01. And then you times it by 100 to get the percentage of carbon. Likewise, you would do the same thing for hydrogen, where you find the grams, how many moles of hydrogen. There's 6 of them. Each hydrogen is 1.01 grams. And so you multiply the 6 times the 1.01, and that will give you 6.06, divided by the whole, and that will give you the percent of hydrogen. Now, notice when you add up these 2 percentages, the carbon and the hydrogen, they should add up to the whole, which is 100% of this whole compound. So that's percent by mass. Okay. Now we go to the next set of problems. In the next set of problems, you're given percentages here, and you're asked to find the empirical formula. So you're asked to find this empirical formula from the percentages. So it's going backwards, okay? So how do you find the empirical formula from the percent composition? To do so, you start off with that first problem. The first problem says you're given 92.24% carbon and 7.76% hydrogen. The first thing you need to understand is percentages are based off of 100. So it's ratioed to 100. So you're looking at 100 grams. What you want to do is you assume 100 grams of this unknown compound that has carbon and hydrogen. We don't know what X is yet. We don't know what Y is. We're trying to find those 2 mole values, moles of carbon and moles of hydrogen. So the first thing to do is once you assume 100 grams and you know that 92.24% of that mass is carbon, that means 92.24 grams of it is carbon. So you convert that grams to moles because X represents the moles of carbon. So let me write that and remind ourselves that this is the moles of carbon that we're finding here. And then we would do the same for hydrogen. We would convert the grams of hydrogen into moles of hydrogen. Then that will give us our Y. Then we plug it into our formula, X and Y here, and we'll notice that this formula we have never seen before as partial decimal place numbers like this. So we're then going to divide it by the lowest molar value. When we do that, we then get a formula that looks like this. Notice the ratio. It's a 1-to-1 ratio between carbon and hydrogen. This is the most reduced form of it, and so this is called the empirical formula. Please rewatch this video if need be, and slow down to the parts that you need a little bit more help on, okay? Bye-bye.